Welcome back to one of these Spanish-speaking acousticians in the Americas events from the regional chapter. We will do a short introduction in Spanish, and then the talk will be in English for everybody. Thank you all for being with us. Please use the Q&A button, which is down there, for questions, and the chat on the left side to share any comments. Bueno. La Acoustical Society of America, en su capítulo regional de Spanish Speaking Acousticians. En esta ocasión presentaremos una charla muy interesante sobre aislamiento de vibraciones por un querido amigo que se llama Jim Sadler, que trabaja desde ya hace varios años en Mason Industries y Mercer. Estas ambas son empresas norteamericanas con trayectorias de más de 60 años en el mercado. Son empresas que fabrican elementos para tratar el ruido y las vibraciones. Pasando un poco a nuestra misión u objetivo del capítulo, nosotros pues, nos queremos congregar y conectar profesionales y estudiantes de la acústica y el sonido en el área geográfica de América Latina. El capítulo actúa como un nexo entre la Acoustical Society of America, ASA, y los hispanoparlantes interesados en la acústica y el sonido, desarrollando y divulgando actividades de interés para sus miembros. Tenemos actualmente una membresía y una distribución geográfica que está conformada por 242 miembros aproximadamente, de los cuales hacen presencia en 4 continentes, 24 países, donde la mayor representación está en Colombia, México y Ecuador. Tenemos 43 miembros que hacen parte de la ASA. Discutimos aproximadamente entre 13 áreas técnicas y las principales tratan de acústica arquitectónica, ingeniería acústica y de ruido. De estos miembros, 60 son estudiantes. Les presentamos un poco nuestra mesa directiva, que está conformada por nuestra presidenta Mariana Botero, nuestro vicepresidente que es Felipe Rayman, tesorero tenemos a Zachary Littlin, secretario tenemos a Juan Francisco Mayorga, nuestra representante a nivel nacional ante la ISA es Ana María Jaramillo. Y como miembros de la Junta General estamos Andrés Millán, Brian Moisés Rodríguez y yo, Diego Alejandro Suárez. Bueno, para unirse al capítulo y para hacerse miembro del capítulo no hay que ser miembro de la ISA, tampoco existe ningún pago de membresía, únicamente deben ingresar a nuestra página web en el enlace de Únete y hacer el registro. Ahorita podemos ponerlo en el chat para que lo tengan presente. Constantemente estamos buscando nuevos miembros que quieran hacer parte de la junta directiva. Entonces, simplemente es que nos escriban al correo, al Gmail, y nosotros les mostramos cómo trabajamos y si están interesados, bienvenidos. Les compartimos nuestras redes, contamos con página web. Tenemos un Facebook, un LinkedIn, tenemos un canal de YouTube para ver los eventos que ya hemos realizado. Están abiertos a disposición y los pueden ver cuando la presentación está en inglés. También se puede ver con traducción simultánea al español. Todo esto quedó pregrabado. Y por último, nuestro correo electrónico, donde constantemente estamos enviando noticias y eventos a presentar. Les contamos que actualmente la competencia Royster consiste en que el capítulo convoca a los estudiantes a participar en un concurso. Es acerca de una beca estudiantil para proyectos sobre ruido y audición. Tenemos un premio de $2.500 para cubrir los costos de estudio de posgrado. En caso tal de que el póster tenga varios autores, el premio se divide entre el número de estos. Los aspirantes son estudiantes tanto de posgrado en programas de acústica o afines, o también pueden ser estudiantes de pregrado que vayan a cursar un posgrado en acústica o afines. Las reglas, pues generales, tenemos acá, está presentar un póster de control de ruido o conservación de la audición. Estos autores deben prepararse muy bien para una presentación en conferencia virtual con el panel de jueces. Mínimo se deben recibir 5 aspirantes, 5 proyectos participantes. De lo contrario, se puede posponer o cancelar la competencia. Los ganadores deben enviar una copia del proyecto de tesis mínimo en un tiempo de 3 meses próximos a su graduación. También les vamos a poner este link para que encuentren más detalles de esta competencia Restraint. Es muy interesante. Para cerrar este semestre, ya tenemos varios eventos confirmados. Uno que es el 12 de abril a las 3 de la tarde, hora Bogotá, Lima, Quito. Es de Machine Learning in Underwater Acoustic Classification and Tracking. Este lo va a dirigir Andrew Bernard, Stephen Whitaker y Timothy Havens. El 28 de abril, a la misma hora, tendremos también difusión acústica por Alejandro Biondo. Muy interesante para los amantes de la acústica. El 10 de mayo a la 1 de la tarde, hora Bogotá, Lima, Quito, tendremos sala de concierto forense, identificación y solución de eco problemático. Algo muy nuevo pues para mí personalmente. Y este lo va a dirigir Henry Ashburn y David Conant. El 31 de mayo a las 3 de la tarde, Bogotá, Lima, Quito, tendremos la situación del mercado y acústica en México por Alejandro Ramos y Jessica Zamudio. Y ya para cerrar, tener en cuenta que respecto a la competencia Royster se van a terminar de recibir los pósters el 27 de junio. Bueno, este webinar será presentado en inglés. En la parte de abajo de la pantalla de Zoom se puede escoger el canal de interpretación simultánea al español. El audio original bajará el volumen y se puede escoger apagarlo por completo si ustedes lo desean. Por favor, usar el botón de Q&A para hacer preguntas y el chat en caso que tengan algún comentario. Voy a pasar ya a inglés para que, por favor, todos los que quieran escuchar la traducción al español, hagan ya mismo el switch. Okay. Well, now we're going to start our talk in English. So let me make a short introduction about Jim Sadler and his background. Well, Jim Sadler is the Vice President of Sales for Mason Industries and Mercer Robert. He started at Mason following his graduation from Villanova University in 1990. He's a registered professional engineer in the state of New York and holds a master's in business administration from Hofstra University. He has extensive experience in the application of vibration isolation, architectural acoustic, and seismic restraint systems. On our schedule, Jim will deal with different topics such as discussion of vibration isolation, seismic restraint, architectural isolation, and flexible connectors. So, Mr. Jim, thank you very much for being with us. How are you?
Thank you so much.
Okay, Jim, so it's a pleasure to have you here. Right now we have more than 25 participants. So the panel is all yours.
Thank you so much for your time and the introduction, Diego. I really appreciate that.
It's a pleasure. I'm gonna start my sharing screen.
You ready to go?
Yeah, I see your screen. Yeah.
Okay, great. Outstanding. Well, thank you so much for your time. And first off, let me apologize. As Diego mentioned, I don't speak Spanish, and I'm sorry for that. I will try to watch my cadence so the interpreter can keep up. I know that's a challenging job, especially when we're talking technical aspects. Also, some of this material will be familiar to many of you. So I apologize for the simplicity. I'll try to introduce many project examples. And of course, if you have any questions, please stop us. Or I'm here with Ian Azrak. Many of you know he's off screen. I don't know if you want to poke your head in. Ian will also help interpret, and either of us are available for questions or follow up after the discussion. So my first slide is a schematic of a simple vibrating machine. And any machinery, as you're familiar, has some type of massive unbalance. And as the mass rotates down, it wants to push the equipment into the structure. And as it rotates up, it wants to pull the equipment off the structure. And this vibration force can be disturbing, both from simple vibration, but it can also create sound throughout the building. That vibratory force is proportional to its distance from the center of rotation, directly proportional. It's directly proportional to the size of the mass. So if the mass doubles, this force doubles. And it has an exponential relationship with the speed. So if the speed is twice as much, the force at the structure is 4 times as great. And I have here a little demo, little fan demo. It has a massive unbalance on it. Little bolt through the fan wheel. I've got to be careful when I turn this on. You'll see why. Really, the most dangerous part of my job is this demo kit. And I have my simple vibration meter here, a glass of water. I know you can't feel the vibration from halfway around the world, but you'll see this glass shake. So I turn the fan on. Creates a vibration. You can see the glass shaking. With a small increase, you can see with a small increase in speed, the force goes up quite dramatically. I could actually shake the glass off the table. And some builders who are inexperienced or don't have the information would assume that if I bolt this machine down hard enough, that I can reduce this vibratory energy, right? We've all experienced that. So I can lean on this machine. I can lean on this machine, but you still get 100% transmission, right? So again, that rotating massive unbalance is shaking the table, creating all kinds of noise and vibration. And what we want to try to do is isolate the machinery to reduce the vibratory force reaching the structure. So if we place a resilient element between the disturbing machinery and structure, we can reduce that vibratory force. Again, a lot of us are familiar with the efficiency equation, which tells us as a simple percent reduction, how much vibratory energy we can keep out of the structure. And it's dependent on 2 variables. One is the driving frequency of the machine, or the operating speed, F sub D. And one is the natural frequency of the supports. And the efficiency is shown on the screen. It's 100, which simply makes it a percentage, times 1 minus 1 over FD over Fn squared minus 1. And again, the F sub D is a driving speed, driving frequency in RPM. And the natural frequency is the frequency the supports want to bounce out if you put it into motion. So driving frequency is very simple, right? We simply read that off the equipment submittal. Natural frequency is a little trickier, and I promise there's only 2 equations in this whole presentation. Right, this is the second of two. So natural frequency is a little trickier. Natural frequency is 188 times radical 1 over D, where D is the deflection of the isolator, how much the isolator deflects under load, how much it squishes. I don't know if there's a Spanish translation for squishes. I could use that directly, okay? So by knowing the deflection and plugging that into the formula, we can determine the natural frequencies, again, in cycles per minute. So if you have a 1-inch deflection system or 25 millimeter, if we translate it, the 1 would be 25 for metric. Either way, we get 1 over 1. Radical 1 is 1 times 188. The natural frequency for a 1-inch deflection system or 25 millimeter is 188 cycles per minute. So if I put a mass on a spring, deflect it 1 inch, 25 millimeter, and give it a shove, it's going to want to bounce up and down 188 times in 1 minute. For a 2-inch deflection system or 50 millimeters, the natural frequency goes down to 135 cycles per minute. 3-inch, 109 cycles per minute. 4-inch or 100 millimeters, it's 94 cycles per minute. So as deflection increases, as my isolator deflects more and more and more, the frequency goes down, the natural frequency decreases. So for a given system, as the natural frequency goes down, this ratio gets higher, and I get a higher and higher isolation efficiency. So simply put, the more isolator deflection, the less transmission to the structure. So going through the hierarchy of isolation material, you may be familiar with this cork pad. That was the first isolation media used, right? And we still sell it. It's very stiff, very little deflection. Then you'll see I put it on cork. No reduction at all. No reduction at all. Now the demonstration is rigged in my favor, right? Because this only weighs 100 kilograms. but these isolators can support much more weight. All right. Actually, this weighs about, I don't know, 5 kilos. Yeah. 5 kilos. But these isolators can probably support 20 to 30 kilos. So there's very limited deflection in this demonstration. But even in real world applications, this pad's only designed for 1 millimeter?
1/8 inch.
Yeah, yeah, maybe 1 to 3 millimeter deflection. Very limited deflection. Something a little bit better is a super W pad. You probably can't see it in the camera, but it looks like a waffle. What's this in kilos? Capacity 180 pounds.
180 pounds. 80
kilos. Okay. So this can support 80 kilos, this little tiny pad. 100 millimeter by 100 millimeter can support 80 kilograms. It's going to deflect about 5 millimeters, 5 to 10, between 3 and 5 millimeters. Okay, so a little bit better than the cork, but still not, it's not going to affect this at all. Something a little bit better still is going to deflect a little bit more is the ND mount. So what I'm doing now is just showing you the hierarchy of isolators. So worst performance is cork pad. A little bit better is a 3/4 inch thick super W pad. A little bit better still is a rubber mounting. It's going to deflect maybe 12 millimeters under load. And it's only, this isolator's capacity is maybe 10 kilograms. Then we get into steel springs. And steel springs are going to deflect anywhere from 25 millimeter to 125 millimeter. So with the spring, we will get some appreciable deflection with the demonstrator. Okay, you'll see the effect. Ian, can you feel any vibration?
Nope, can't feel anything, Jim.
At least $20. Okay, so what's happening from a physics perspective is that the springs want to bounce up and down again at that close to 188 cycles per minute. This is rotating, I don't know, 1,000 cycles per minute. The springs, the natural frequency of the springs can't react to the driving frequency of the fan. And it's counterintuitive, at least to me, it's counterintuitive. But the higher the RPM, the less amplitude at the frame. So this is deflecting maybe 12 millimeters under load. This is deflecting 12 millimeters. But the amplitude here is much less than a millimeter. It's just a blur. The bass is just a blur. This is not bouncing up and down 12 millimeters. And it's somewhat counterintuitive, but the softer the springs, the more deflection you have into the springs, the less amplitude you get at the frame. You can go up and push it, and it'll move more. A higher deflection. Make sure I'm in camera. Yeah. Stationary. You can get into a resonant condition. Now the driving frequency is close to the natural frequency of the supports. I might be able to do it better on this. So that's resonance, where the driving frequency is getting close to what the springs want to bounce up and down at. But you notice when you speed it up, you get out of the resonant condition, and now the bass is stationary. For heating and ventilating systems, we only have to really be concerned with resonance with large fans and cooling towers. So for those systems, we recommend very high deflection springs, 3, 4, 5-inch deflection springs. Okay, so the efficiency, this whole idea of efficiency, and a rule of thumb is that if the driving frequency, the operating speed of the equipment is 3 times as great as the natural frequency of the supports, you're going to eliminate 90% of the isolation from reaching the structure. So way back before I started, that was a common specification that all isolation was to be 90% efficient. So the efficiency gives us some direction, but it's not complete. And what it doesn't consider, one of the important things it doesn't consider is the structural deflection. So this system works on this table, because the table is very stiff. This table is very stiff relative to the spring supports. If we had this on a trampoline, the trampoline would be so soft relative to the springs that this wouldn't, Ian was supposed to bring the trampoline, he forgot. But if we had a trampoline here and we put this system with the springs on a trampoline, the trampoline's so soft that the springs wouldn't be nearly as effective. Okay, it's not as bad in structures, but we do have to consider the structural deflection. And we found this in real world applications. When we had equipment in the basement, we put it on isolators, even cork pads, it worked out great. You take that same system and put it in the top of the structure where there's a structural deflection, those systems are no longer effective, and we had a lot of problems. So we learned this a long time ago with our acoustical friends. So the other problem is it doesn't take into account the equipment size. So if I say isolators are going to be 90% efficient, if I have a small exhaust fan, that's probably more than you need. But if I have a huge exhaust fan for a computer chip facility, we see those all the time in computer chip facilities, big, 60-inch wheels, the fans are as big as this room, then 90% is insufficient because that larger equipment is going to create a lot more vibration. And with a computer chip facility, as an example, it's a much more sensitive application. So 90% in that example would not be adequate. So the efficiency theory gives us some direction as to how these systems work, but from a design standpoint, there's some significant weaknesses. So what do we do? How do we approach this? Now we have a lot to think about. I didn't really get into, we kept it very simplistic because I barely got through vibrations in college. We only used 2 equations, but it can get very complicated, right? We remember 2 degree of freedom systems. We have structural deflections to consider. We have the sensitivity of the occupants within the space to consider. So we wanted to provide a relatively easy way to select vibration isolation, right? So many years ago, we developed a selection table that's also been used by ASHRAE, which is the American Society of Heating, Refrigeration, and Air Conditioning. So in their vibration, sound and vibration chapter, they'll have a similar selection table. And they all function the same way. You have equipment along the left-hand side of the table, and across the top, you have various structural spans going from ground supported. You have a 20-foot span between, and that's what I'm saying is the span between the columns, the span between the support columns within the building. So you have ground supported 20-foot or 6 meter, 30-foot, 9 meter, 12 meter, then 15 meter. And then you have the possible structural deflection, 17 millimeter, 25 millimeter, 34, and 42. So that's how much the structural engineers will allow those floors to deflect at those spans. So by knowing the equipment and the structural span, we can very easily select the appropriate isolation. So as an example, if I had a base-mounted pump, which are found towards the bottom of this section, and by the way, this is an excerpt from a much larger manual. This is just a selection table. Ian will be happy to get that if you have interest. We're getting back to the selection of base-mounted pump, and let's say I put it on an upper story with 9 millimeter structural span. I simply read down, I'll see the letters B, L, and O. Those correspond to the products we recommend. And to the right of that is the recommended static deflection, in this case, 65 millimeters. So that's how much we're going to select the isolators to deflect 65 millimeters. And you'll notice that regardless of structural span, the recommended isolation system is the same. The only thing we've changed is the static deflection of the isolators. That's increased with structural span. We're compensating for that structural span by going to higher deflection isolators. So following that example through, spec letter B is a freestanding spring. Spec letter L is a concrete base. And spec letter O is an elastomeric flex connector. So here's what that would look like in the field. You have a end suction pump supported on a concrete base. The base is supported on springs, and we have flex connectors at the suction and discharge. And the base is there for rigidity, not for inertia. We often call it an inertia base, but in the case of the pump support, you can't support a pump directly. The pump frame is not designed to be point loaded. And the pump frame will rack if you do that, and you'll wear out the couplings. So the base provides rigidity, and then that frame can then be point supported on isolators. Here's an inline pump, same idea. This was outdoors in San Francisco, so we have a seismic snubber as well. We'll get into that in a little bit. But you see that same concrete base and the flex connector at the suction and discharge. I may pass over some of these. From a consultant standpoint, just be careful of the isolation provided by some of the equipment manufacturers. Commercially speaking, we love to sell to those groups, but their material does not always match or does not always meet your specification. Sometimes it does, a lot of times it does not. And this is just an interesting application. One other thing to be concerned about is a lot of things that may not be specified. So in this case, this is a cooling tower, and the cooling tower manufacturer was working with the contractor, and they said that, oh yeah, we can point load this tower. We recommended that the tower has a steel, which typically does, has a steel base between the tower and the isolator. We walked away from this project. We didn't want to do it without the steel frame. They found someone to point load it. This tower should not look like this. Okay, so sometimes it's not only what's specified, but the experience of the people providing the material is also critical, as you can appreciate. Okay, then we get into seismic. So up to this point, we have a piece of equipment that's free floating. Everything's great. You know, it's free floating. It's no oscillation. Everything's super. But then when an earthquake comes, if an earthquake comes, then you have the equipment free floating. Okay, you can. Well, it's actually holding up pretty well, but you can. The structure can resonate with these springs and throw the equipment off the springs in a seismic zone. So in a seismic zone, from an engineering standpoint, we want it fixed to the structure. But with acoustically, we don't want that. We want the equipment free floating. So with seismic and isolation, we have two conflicting systems that have to work in concert together. Conflicting goals. So this is a video, if I can get it up. This is a video of a shaker table test. This is a cooling tower on a shaker table. It's on spring isolators. I know you can't, spring isolators are down in the corner. And it also has seismic snubbers built in. So you may have the same requirement where you are if you're in a high seismic zone, but in the United States, in California, they insist that the equipment survive a simulated earthquake. So they take the equipment, they put it on a shaker table test, they bring it back to their factory, make sure it's operational, and if it is, it passes the test. So this is just a video of one of those tests we were involved in. This is a cooling tower on a shaker, simulating an earthquake. This is a designer. If the tower falls on them, the test fails. So that's what happens with an earthquake, right? So if you have something on isolators, it's going to bounce around. So the idea is to add some other damage from earthquakes. So Loma Prieta and California back in the 90s, just some mechanical damage. So those of you in seismic zones, you have an additional challenge, right? You want the system isolated, but you also want to incorporate seismic snubbers that keep the equipment in place in the event of an earthquake. So there's another selection table for seismic zones. So that same pump we looked at for isolation, now let's put it on a high seismic risk area. Well, we're going to have numbers instead of letters to designate the equipment we recommend. And in this case, it's 5, 16, 21, and 23. Those correspond to the products, which I'll show you in a moment. And then again, to the right of that is the recommended static deflection of the isolator. So again, same spring, that hasn't changed. Same concrete base, that hasn't changed. Same flex connector, no change there. The only thing we've added in a seismic zone is a seismic snubber. There would be 4 of these on a typical system. From an acoustical standpoint, the way this works, this would be in the corner of the base. You'd have an embedded bolt that passes through an angle with a large rubber grommet. And there's an air gap there. So during normal operations, this bolt is not in contact with the external component. So the equipment remains isolated. When an earthquake hits and this base is bouncing around, that's going to this assembly is going to restrain that base in all directions, because you can't anticipate how this earthquake's going to jostle the building and everything in it. From a specification standpoint, you don't have to be concerned. This snubber comes in several different sizes. One could fit in the palm of my hand. One is about as big as a laptop computer. All you're doing in specifying this is giving the contractor some direction as to what your requirement is. We're going to do the seismic calculations that many of you are familiar with, that you've seen. We're going to determine the appropriate size of the snubber based on code factors. And we're also going to determine the size of the anchors that's going to keep this equipment in place in the event of an earthquake. Okay, so that covers the basics of vibration isolation and seismic. One important aspect with vibration, and really the best isolator we can provide, is an air spring. What can happen with high-speed equipment operating at 3,600 RPM, 60 Hertz, is that despite the theory, if you put the equipment on steel springs, that high frequency energy will travel down this coil like a water slide and get into the structure. With an air spring, we have a rubber bladder that's capped on the top and bottom, and there's pressurized air inside that supports the equipment. And the advantage is it has a low natural frequency, but the other advantage is that high frequency noise cannot get through this rubber bladder. There's too much impedance. Okay. For seismic zones, we can put that same air spring in a housing. And again, now we've orchestrated the isolation and the seismic restraint, where we have that conflicting engineering requirement. But when we put that air spring in a housing, we've got both the isolation and the seismic restraint covered. This restraining assembly is designed so it's not in contact during normal operation. But like the snubber, should the equipment move, this housing will keep the equipment in place. So as an example of that, this shows a project in Chicago. They had an air-cooled chiller above a very high-value condominium. Initially, it was on steel springs shown on the left. They weren't ours, but they were fine and would have met its specification requirement. But they had a terrible noise problem in the space below, in the condominium below. So we replaced that. We replaced the steel springs with air springs, and there was a 15 decibel reduction in noise in the occupied space right below this air-cooled chiller. These photos show it during installation. It comes with a constant air supply, because like your tires, the air springs will lose air. So it's typically supplied with a leveling system. And these couple of photos show it as it's being installed. The one on the left is before the piping gets installed. The one on the right, it's all piped up and ready to go. So there's a funny story with this. We had a tremendous reduction. We work with the acoustician in Chicago. There was a tremendous reduction in noise, and many of you will appreciate this, but the occupants could still hear it. So we went back to look at the isolation system, and it was functioning well, no problems there. But in doing the examination, I was looking around, didn't know what to do. The system was working well, but we noticed all these PVC vents around the chiller. So the airborne noise was going right down to the vent into the space. So we tackled the structural borne vibration and noise with the air springs, but we still had an airborne component. So we found some gypcrete, some sheetrock and caulk, and we covered one of the vents. And that solved the problem. That was it. Of course, we couldn't leave it sealed because we didn't want to kill the people inside. So we took that off, and they built it. They made the vents higher than the air-cooled chiller. And that's solid. This is another example. This is a centrifugal chiller. This is at the Twitter headquarters in San Francisco. And Twitter moved from the suburbs downtown, and they took over what had been a furniture store, very large furniture store. And this chiller was right above where they were having where they were building an auditorium. And it was on steel springs, which again would have met really anyone's recommendation for the most part, right? But they had terrible noise in the space below. So they replaced the steel springs with air springs, and this is during that transition. And this is one of the rare instances where we begged the acoustician to provide before and after results, and they were able to do that. As you can appreciate, usually when you solve a noise problem, there's not much enthusiasm for doing a follow-up test. But in this case, we got it. So what this table shows is the noise in the space below that chiller. And the gray line is the maximum noise level with the steel springs. And the yellow line is at the full chiller load again on the air springs, the yellow. So that's about a 25 decibel reduction at 125 hertz. And you can see the ambient noise level. It almost reaches the ambient level with, that's with the chiller off. So you realize a tremendous reduction in noise with air springs. It's really the air springs are the best system we can provide. This is just some of the same information with the NC curves. So we went from an NC 65 down to an NC 30 with the introduction of the air springs. And keep in mind that, again, that chiller was isolated. It was isolated on steel springs. We didn't realize this improvement until those were replaced with air springs. Another aspect of air springs is that if you have a large enough diameter and enough air springs, you can support anything. This shows an air spring. These were 1 hertz natural frequency, and they supported a 1 million pound, what is that, about 300,000 kilos, thereabouts, no more than that.
450,000 kilos.
Yeah, so that's right. So this is 450,000 kilos, this concrete base, and it's supported with a series of air springs. You can get an idea how large they are. There's a barrel at the end of the row here to give you some proportion, and then a doorway. So these are quite large, but if you have enough diameter and enough pressure, you can lift anything. You can support anything. And this was a very sensitive scientific application where they didn't want any ambient vibration to get into this test facility that was supported by this large concrete block. Okay. One of the more common problems that we run into quite frequently is a disturbance known as blade passage frequency. And it's associated with pumps, and the pumps are putting pressure pulsations into the water column at a rate equal to the blade passage frequency, a term that I know you're familiar with. And what can happen is that blade passage frequency can resonate with pipe hundreds of feet from the pump. And a classic example is shown schematically on the screen, where we had pumps on the 27th floor of a building, pumping water to chillers on the 16th floor mechanical space. And on the 18th floor, they had a terrible ringing in the space. And an acoustician came to visit. It was actually Fred Shen of Shen, Milson, Wilkie, if you're familiar with a fairly large firm in the States. At the time, he was with Cerami, another a large firm here in New York. In any case, he came in and took the measurements. And the pump was isolated. It was on a concrete base with springs, just like we discussed. There were no flex connectors. And he advised them, well, you have to introduce flex connectors at the pump. And they thought he was crazy because, remember, they're on the 27th floor. There was no disturbance on the 26th floor, 25th, et cetera, all the way to the 18th. So how would putting flex connectors up here affect the noise level 9 floors away? But by introducing those elastomeric, those rubber connectors, you reduce the noise by 10 decibels on the 18th floor. And the reason it works is that elastomeric connector can expand volumetrically with that pulsation. It knocks it out. It knocks out that standing wave. Again, it's not traveling through the pipe wall. It's traveling through the water column. It will also reduce any high frequency noise that's traveling through the pipe, just like the air spring knocked out that high frequency machinery noise. This will do the same thing. So you have the blade passage frequency disturbance traveling through the water column, but you also have high frequency noise traveling through the pipe, and that rubber body will stop that. And it will also reduce mechanical vibration. Oh, my set for time. Okay.
4:30.
Okay, great. Okay, so that covers in a relatively fast way both mechanical vibration, seismic restraint, air springs, which is again the optimal isolation system we can provide. We talked about elastomeric connectors. Now we're going to get into what we think of as airborne noise. So I can isolate my fan, no vibration, but I can't hear myself because of all the airborne noise radiating off the equipment. So you can do a great job isolating the equipment, but you still get airborne transmission. So this is a simplistic slide of the mass law, which you're more familiar with than me, but the way we think of it, we know that if we double the mass of a structure, we can realize a 5 decibel reduction in noise transmission. Very simplistically, right? The simplistic view of it. So that's barely perceptible, right? If we double the mass again, we go from 12-inch to 24-inch, we pick up another 5 decibels. And we understand that if there's a 10 decibel reduction, it's about half as loud as the original condition. So if you have a 150 millimeter structure, thanks Ian, and you double it to 300, and then you double it again to 600, you're going to get half as loud as the original condition. But no structural engineer in the world wants you to increase the slab thickness from 150 millimeter to 600 millimeter, right? Not possible. So a more efficient way to do that is to introduce an air gap between 2 structures. So, and we call this the floating floor. We call it a floating floor, but really, as you can appreciate, the air gap between the floating mass, floating concrete mass, and the structure, that's what's providing the isolation. If we could levitate this floating floor without any supports, that would be ideal. But not practical, right? We need some type of way to support the floating floor to create that isolating air gap. So there's two methods of doing that, two methods to create the air gap. The first is what we call a formwork system. Oh, let me go back, I'm sorry. So if we have no supports, that's the best, but not practical, right? So we want as few a number of supports as possible. And we also want them to have a very low natural frequency so they don't transmit sound across the air gap. Because the supports are a necessary evil. So as few as possible with as low a natural frequency as possible. So there's two ways we do that. There's two ways we create the air gap. One is what we call a formwork system. And in this case, you know, shown in the drawing here, we lay out these rubber discs. They're 50 millimeters tall. Typically, we can do taller ones, but more often than not, they're 50 millimeters tall. 50, that's what I said, yeah, 50 millimeters tall. And so these are laid out at about 600 millimeters on center between them. Then there's plywood that's placed on top. Then a plastic sheet, and then the concrete. So the height of the mounts creates the air gap. The height of the mount creates the air gap. But with this system, we're running, again, about 600 millimeters between supports because we're limited by the plywood. The plywood has to be supported. We can't have the plywood sag under the concrete. And this is an okay system, but one of the primary weaknesses of this, despite everyone's best efforts, the people who pour concrete are generally, they're not ballerinas. Okay, they're up there with hoses and rakes. They're pouring this concrete as quickly as they can, and despite everyone's best efforts, sometimes concrete gets through the plastic into one of these gaps and creates a stalactite across the air gap. We've had this happen to us, and it short circuits the entire floor. These are some typical mounting. So with that system, we call it the EAFM. And they're designed for about 8 millimeters of deflection. And at that deflection, the natural frequency is about 6.5 hertz. The better way, the preferred way to create that air gap is after the concrete's cured. So with these mounts, this is called the jack-up system. It's an FSN system. With this system, we eliminate the plywood. The mounts are placed at 1.5 meters, about double what it is for the formwork system. They're placed directly on the plastic sheeting to create the break. Yeah, I'm sorry. Yeah, on top of the FSN is placed directly on top of the plastic sheeting. The mount incorporates a dog ear that the reinforcement is tied into and supported from. That's a tough translation, dog ear.
Yeah, he got it.
Okay. The concrete is poured up to the top of the mount. It comes with a rubber plug. I didn't show that. Usually comes with a rubber plug initially at the top. That screw is not there initially. Once the concrete cures, you pull the rubber plug. You insert the jack screw and you actually have these T-wrenches and you lift the floor up, creating the air gap. So with this system, we have 1/4 the number of supports as we do with the formwork, approximately. And there's no chance of concrete getting into the air gap. So this is the preferred way to do it. We've done thousands, if not tens of thousands of applications like this. Okay, more recently, we've upgraded the elastomer, this part, the supporting rubber, from neoprene to natural rubber. When I showed you the natural frequency equation before, we were assuming a spring where there's no damping, or very little damping. With rubber mounts, it's different. You can't plug in the static deflection into that equation to get the natural frequency. You can't do it directly. You have to correct the deflection by what they call the dynamic stiffness correction factor. So those factors are much higher for neoprene, which is what we initially built the mounts for. It's kind of a long story, but yeah. So those values are higher for neoprene than natural rubber. So we realize a lower natural frequency with natural rubber than neoprene because of the lower dynamic correction factors. So with neoprene at 6.7 millimeter deflection with a 40 durometer, which measures the hardness, the neoprene has a natural frequency of 7.2 hertz. The natural rubber goes down to 6.2. At 60, it goes from 8.9 down to 6.5. So the natural rubber provides a better isolation material than the older neoprene. So just a recent upgrade, that's all. Fiberglass is another material. It's a much higher frequency. It's always used with a formwork. The spacing is about 1/3 to 2/3 of a meter. And the isolation frequency, the lowest published, is about 12 hertz. Should I discuss Entrapped Air? You think, Ian? I'm just conferring with my associate.
Briefly.
Okay. One of the topics that comes up often is entrapped air. So when you look at a floating floor, if I can go back to this slide, so that we discussed the mount frequency, but there's a thought that the air gap has a frequency of its own in the absence of, or in parallel with the mount frequency. And that frequency can affect the performance of the system. And I'll say it's theorized that air gap frequency is dependent on the air gap thickness and the weight of the slab, weight of the floating slab. In my experience, I haven't run into any problems with entrapped air. Well, one time, I had a floating floor about as big as this table, and it was very thick. I don't know, maybe 2 feet thick. That's about this thick, and it was on springs, 75 millimeter deflection, and it was supporting a classified piece of machinery at a military base. I didn't even know what it was. and the surrounding manufacturing space came up to the edge of the floor, edge of this isolated floor, with a piece of foam between the isolated slab and the surrounding structure. So when the acoustician measured the natural frequency, they were expecting a frequency of 135 cycles per minute. No, I'm sorry, 109 cycles per minute. And it came up higher than that, maybe 20% higher. And we traced it to this air gap frequency because in that situation, the floor is so rigid, it acts like a piston. So in that particular instance, we removed the foam between the floating slab and the surrounding structure to vent the air. And that solved the problem. But with most floating slabs, they're relatively thin. They're only 100 millimeters thick typically, and they're surprisingly flexible and large in area. So if you have a displacement on that corner, the air moves laterally through the air gap. It doesn't act like a piston. But if there is a concern, again, the theoretical natural frequency of the system is the sum of the squares. So if you take the frequency of the air gap, square it, and that's determined with this table. And we could send you this whole paper if you'd like. Plus the frequency of the support squared, and then you take the square root. That's going to give you the system frequency. So if you have a particularly sensitive application, it's something to consider. And of course, you can't really affect, you can affect the air gap frequency slightly by venting. But then you're creating a pathway for noise. So it's one or the other. Okay, the other aspect is the structural test. On occasion, there's concern if people don't have a familiarity with the system. There's a concern that the floating slab might crack. This was more of a concern when we introduced this system back in the 70s. So we actually conducted a series of tests structural tests on floating floors. You can tell it's the 70s by this gentleman's plaid pants. And the bell bottoms. Okay, but anyway, we conducted a series of structural tests. So one of the more interesting tests, I think, was we were able to load a floor with, help me with the kilograms again, it's 2 point.
That would be 4,500, about 13,000.
I have my kilogram to pound conversion.
15,500.
About 15,500 kilograms we put on this floor in about a meter by meter area, and it didn't fail. So the idea being that these floors can support a tremendous weight without worry. Okay, when we talk about impact, so those systems I discussed are great for airborne noise, radiated noise off equipment, or people performing between spaces. But when you get into impact, they're not particularly effective. What I mean by impact is weight drops, exercise activity, basketball as an example, dancing. In those cases, we replace the rubber support with a steel spring. So conceptually, it's the same. We're creating the air gap after the concrete cures. But again, the supporting element is a lower frequency steel spring. Very good for gyms, aerobics, that's kind of dated. But dance floors, performance spaces, the spring is the way to go. There's a typical drawing. Oh, and bowling alleys. We've done a lot of bowling alleys on spring systems. So this is a plan view, a drawing of a bowling alley we did in DC above some retail space. And we provide, as we do on every floor, we provide a detailed drawing showing the locations of the mountings, the capacities, et cetera. This is what you would see as a consultant if you specify one of these systems, and we're fortunate enough to go forward. This is the drawing that would be submitted to you for review and approval. Some other details. And then from an installation procedure, we've been through this, but when you get into the space, you snap lines at the grid spacing. You highlight those locations with a little spray paint. You cover the floor with plastic sheeting. Place the mountings down. Rebar gets installed. Concrete's poured. The cover plates are removed. Springs drop down, and these are the T-wrenches. Our workers are on break here. And it never fails. There's always people in your space, right? All these jobs get done, everyone's working at the same time. Gets a little challenging. But ultimately, the floor gets lifted and you create that isolating air gap. This is, I'll skip over this. But we can apply that same idea of a floating floor for sensitive applications. This particular project was for an MRI machine located near a freight rail. And it was a very thick floor, about 1 meter thick, and maybe a half a meter. And this is just a construction of that mount. The reason we needed that depth and that weight for that MRI system is we wanted to reduce the ring time. So when someone walked in, a patient walked in to get into the MRI, the floor would move a little bit. It would not be perceptible to the patient, but it would blur the image. So the idea was to create this big mass to reduce that, how long that would oscillate. Oh, no, that's fine, thanks. And this is what those look like, just to give you the depth of it. And maybe it was close to a meter. Same concept, but a little bit more sophisticated application. And then, of course, we want to create a room within a room, right? So we have that isolating air gap in the floor. We want to extend it to the walls as well and the ceiling, kind of what we look at as a room within a room environment. So the idea is the same. We need supports for those architectural elements. But we want them to have a very low natural frequency so they don't transmit noise across the isolating air gap. And of course, that applies to ceilings and walls, right? So you have various ceiling hangers, don't want to belabor it. Just one last story. This was a project in New York, a very, well, what we would consider an old building for New York, maybe 150-year-old building. And originally it was used for some industrial purpose. Then it was made into living spaces, condominiums, apartments. But there was a nightclub downstairs. Acoustician nightmare, right? So the acoustician in this case recommended an air gap, an isolated ceiling, but they needed a lot of weight to reduce the noise. So he developed a composite ceiling made of plywood, concrete board, with a lot of weight. Now it could not be supported by this older building. They probably could have, but no structural engineer wanted to sign off on it being supported by this older building. Approve it. They didn't want to approve it. So what we did in this case is we used the columns and designed a steel grid work, and it was supported by not hangers, but by more floor supporting isolators. So they built haunches into the column. Those isolators are placed on top. They built a steel framework, and then they built the ceiling attached the ceiling to the steel framework. So an isolated ceiling supported from below. So there's always a way. Okay, that concludes it. There's my very old clip art. So we appreciate your time. If there's any questions, we'd be happy to try to answer them.
Thank you, Jim. We already have one question from Zach. He say, "Hi, Jim. Sorry, I'm coming in late and I may have missed something. Do you ever get pushback on flooring MRI room floors with metal springs from MRI manufacturers? If so, what can you offer them to address concerns?"
We do, and on that one project I mentioned, that was a concern. And in discussing it with the MRI manufacturer, they realized that we could work. Initially, they said no steel in the room at all, but they had such a terrible vibration problem. We had to come to some compromise. So they told us to stay out of a certain envelope around the MRI, maybe 2 meters away. So our isolators weren't at the standard spacing. We placed our first isolators outside this envelope. And that's usually the way it goes. So there is pushback.
And they cover the floor sometimes.
Yeah, so and there's shielding as well. Sometimes it's enough, sometimes it's not. So it's a give and take with the MRI manufacturers.
Well, Zach, hope to answer your question. There's no more questions. Fernando says, "Great presentation, Jim. What are your recommendations for a room within a room when the inner layer is gypsum board? How do you support the drywall?"
We do have a support for drywall. Let me go back. This clip is what we call a DNSB. I know this shows concrete block. This can also be used for drywall, as can this wick. And we're coming out with a lighter weight isolator. We've run the testing. We've got the fire rating on it. We just have to come out and announce it. But So there'd be three possibilities: the DNSB, the WIC, and this product that is forthcoming.
Great, thank you. So, I'll check the comments. There are no more questions. Okay. I think it's done. So, Jim, thank you very much for your
Thank you so much.
to share your presentation with us. Many things, very extensive. So hopefully we have this video, we have the recording in the social media. So maybe they will have more questions there. I will ask you if I can tag you in those, maybe Facebook or
Absolutely, yeah.
LinkedIn. So
I'm not on Facebook, but LinkedIn's okay.
it's okay. Okay. So Jim, thank you very much. We're closing this presentation for today. Thank you for your time. Thank you, Ian, for your time as well. For the group of the Spanish-speaking acousticians. It was a pleasure to have you here. Well, hopefully we will meet soon.
Absolutely, yeah, the next ASA.
And thank the translator, you did an excellent job.
Thanks so
Very good
much.
job.
Yeah, hopefully I was slow enough.
Thank you.
Thank you, Jim.
Thank you, Mariana. Take care.
Thank you. Bye.
For the audience, thank you very much for being with us as well. We will have if you need something, we will have this recording on Facebook soon. That's it.
Thanks, guys.
Great
Thanks
day.
so much for your time. Take
Thank
care.
you. Gracias, Diego.
Bueno, Mariana, gracias a todos por estar presentes con nosotros. Esperamos que haya sido de su interés.